आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
We bring you all a podcast series on STEM popularization, that is, science, technology, engineering, mathematics, and medicine, supported and catalyzed by the National Council for Science and Technology Communication, the Government of India. Program is produced by Media for Community Foundation.
This is Manjeet. Welcome back to the podcast from the Indo French Center for the Promotion of Advanced Research, also popularly known as CEFIPRA. We continue exploring groundbreaking collaborations between Indian and French scientists. Now let's listen to our great scientists for more information.
I'm Binod Sreenivasan. I'm professor and chair of the Center for Earth Sciences at the Indian Institute of Science, Bangalore. I did my bachelor's in mechanical engineering from the National Institute of Technology, Calicut, and then a master's from the Indian Institute of Technology, Madras. After a brief stint as a scientist at the Indian Space Research Organization, I went on to do a PhD at the University of Cambridge. Following this, I did postdoctoral fellowships in France, as well as in England, the University of Exeter and Leeds, after which I moved to India to take up a faculty position at the Indian Institute of Technology, Kanpur. I've been working at the Center for Earth Sciences in IISc since 2012 as a faculty member. My primary research interests lie in the area of planetary magnetism and dynamo theory, and our group in IISc is primarily focused on understanding the principles that govern the generation of magnetic fields in planets like Earth and how they evolve in geological time. So we all know that the Earth has a large-scale magnetic field which is dipolar in nature. So there is a north-south field, and this field essentially protects our atmosphere from the high-velocity solar wind which would have otherwise invaded our atmosphere. So understanding the Earth's magnetic field and its origin is an important scientific objective. However, the Earth's magnetic field has varied in geological time, and there have been deviations from this axial dipole. In particular, there are magnetic flux concentrations beneath Canada and Siberia, and there are equivalent flux concentrations in the southern hemisphere also. And in recent times, in particular the last 2 decades, scientists have noted that the Earth's magnetic north has been drifting from west to east. So we believe that the Earth's mantle has an important role to play in the temporal evolution of the Earth's magnetic field. To understand this, we performed an experimental study under a CEFIPRA project to capture how the lower mantle heterogeneity can affect the Earth's magnetic field by controlling the processes that happen in the Earth's core. So we found that when the lateral heterogeneity in the lower mantle is large, it would control convection in the underlying core of the Earth in such a way that the flux concentrations beneath the Siberian region or the eastern hemisphere of Earth would be more stable relative to the magnetic flux in the west. And this is entirely in agreement with observations. So this, we believe, is a significant advance in our understanding of the lower mantle on the processes that exist in the Earth's core and the generation of the Earth's magnetic field itself. This is very much a project in progress, and we believe that processes in the mantle will propagate all the way through the Earth's outer core and eventually affect the heterogeneity of the Earth's inner core as well. And this is a fascinating idea which needs to be explored, and we believe that this would significantly improve our understanding of the Earth's magnetic field.
Hello. The aim of this study is to understand the role of lower mantle thermal heterogeneity on the dynamics of the outer core. So in this lab we have a simple laboratory model to demonstrate the impact of the CMB, that is the core mantle boundary, on the structure of convection in the outer core, and also to understand how it can impact the structure of the magnetic field, and also how it can affect the anisotropy and the growth rate of the inner core. The geomagnetic field at the core mantle boundary has four main lobes which are situated symmetric north and south of the equator. Now we know that the lateral variations of the core mantle boundary control the structure of convection in the core, and hence the structure of the magnetic field in the core, outer core. Now the aim of this study is to experimentally understand the impact of this CMB on the core. So we have a rotating cylindrical annulus with the same radius ratio of the Earth, and it has two surfaces on the top and bottom, so that we can mimic the dynamics of the outer core at the equator. The geomagnetic field at the core mantle boundary has four main lobes which are situated north and south of the equator. Now we know that the core mantle boundary controls the structure of convection in the core due to its lateral thermal heterogeneity. The present experiment aims to understand the impact of this CMB on the structure of convection of the core, and consequently the structure of the magnetic field, and also how it impacts how the dynamics of the outer core can impact the inner core, like for instance the growth rate of the inner core and hence the anisotropy. So what we have in this lab is a rotating cylindrical annulus, but it's a cylinder, but it can we can use it to understand the dynamics of the outer core at the equatorial plane. And what we do is we apply we divide the outer boundary into four sectors, and we try to mimic the same structure of the core mantle boundary. We heat two sectors and we cool the other two sectors, which is a fair representation of the thermal heterogeneous pattern at the CMB. What we have understood through these experiments is that there is a switch of convection from when we increase the Rayleigh number. There is a switch of convection from the high heat sector to the relatively lower heat sector, and so this was not well understood before, because we know that the magnetic field is stronger under the lower, that is the sector corresponding to Asia, but this was not really well understood before. The convection is normally would be promoted at the higher heat sector, but what we realize is that as we increase the Rayleigh number, there is a switch to the lower heat sector, and this also impacts the structure of the inner core, because we know that the inner core is growing more preferentially on the east side. So so using this experiment, we can get a parameter regime where the the inner core would be growing preferentially on the east side, and also that the magnetic field would be more stable under the Asian sector. So as you can see, the experimental apparatus is behind me. We have filled water already inside, and the water is actually used to represent the liquid core of the earth, and we will study the dynamics of the structure of convection of the water which is filled inside the cylindrical annulus. We have a laser situated around the apparatus with which we can visualize the structure of convection, and for visualization we have cameras which are mounted on the top of the apparatus with which we can measure the structure, the convection pattern which is developed inside. We have wire mesh which are used to heat, they are nichrome-chromium wires which are used to heat the which are used to generate convection, and we also have water jackets which are used to cool the other two sectors. So as I had explained before, there are 4 sectors, 2 of which are heated differentially and 2 sectors which are cooled. The 2 sectors which are cooled are used to represent the African and Pacific sectors, and the 2 which are heated are the Atlantic and the Asian sectors. And we will now start the rotation, so and we can observe the pattern of how it rotates and how we conduct the experiments.
This episode is brought to you with the content support from Cefipra and the technical support from the Sparrows team. We extend our heartfelt thanks to the Director of Cefipra, Professor Nitin Seth and Dr. Payal, for their continuous guidance and support. Stay tuned for more episodes, and thank you for joining.
आइए हम सुने विज्ञान की अनकही कहानियाँ, आइए हम सुने विज्ञान की अनसुनी